All right, hello everybody, it's Arlington Matrix here. Today we're going to be taking a look at angular measure, and specifically, why are radians a unit of angular measure? What do we need radians for? So first, we're going to be taking a look at what units of angular measure are typically found or commonly used that we might already know about. So we'll start off by looking at degrees here. So looking at degrees, degrees are the most common form of angular measure. We pretty much learned that from elementary school, that 90 degrees is a perpendicular, 180 degrees is a half circle, 270 is 3/4 of a circle, and 360 is a full circle. 360 degrees is one full revolution or one full turn. If we take a look at that in regards to this circle that we've drawn here, that means that we have a circumference. A circumference, meaning the outer perimeter of this circle, is equal to 2 pi times the radius of the circle. So if we rearrange that, that means that the radius of our circle is equal to 360 degrees divided by 2 pi. What I like to, personally what I like to do is I like to represent angles in terms of circles, because ultimately a circle is the full representation of an angle, and typically when we represent an angle, we do so using part of a circle. Our radius is equal to 180 degrees divided by pi, and that is the radius of the degree circle. Another unit of measure for angles that you may not be as familiar with is gradians. With gradians, a circle is divided up, instead of 90 degrees, 100 gradians is perpendicular, or is a quarter circle. 200 gradians is a half circle, 300 gradians is 3/4 of a circle, and 400 gradians is a full circle, which is equal to 360 degrees. If we were to take a look at this radius, that would be equal to 200 gradians divided by pi. And finally, we have revolutions or turns. Now this is another one that you're probably quite familiar with, as we tend to see the unit RPM, which is equal to revolution per minute, which is a measure of angular velocity. So with revolutions, a quarter revolution is a quarter circle, a half revolution is a half circle, a 3/4 revolution is 3/4 of a circle, and one revolution makes a full circle. We'll typically see revolutions measured on computer hardware, measured on automotive hardware, pretty much anything that has a rotating shaft. You're going to see revolutions per minute or turns per minute as the unit of angular measure. If we calculate the radius of the circle for revolutions, we get a radius of 1/2 pi. Now let's put this in a handy little table here. So for the unit of degrees, we know that one full circle is 360 degrees, and the radius of that circle is 180 degrees over pi. For gradians, a full circle is 400 gradians, and the radius is 200 over pi. And for revolutions, a full circle is 1 revolution, which is a radius of 1/2 pi. So this begs the question, what happens if we set the radius to 1? And indeed, this is where we introduce the unit of measure known as the radian. So indeed, when we have radius equal to 1, when we set the radius equal to 1, this ends up being pi divided by 2. Why is that? Because the full circle is going to be 2 pi. If r equals 1, circumference equals 2 pi, r equals 2 pi. So that means that we expect this full circle circumference to be equal to 2 pi. If we have a quarter circle, so at 90 degrees here, this quarter circle is going to be 2 pi divided by 4, which is equal to pi by 2. When we have the half circle, that's going to be 2 pi divided by 2, which is going to be equal to pi. That's going to be 3 times pi over 2. That's 3/4 of a circle. And when we get to the full circle, that's 2 pi. Sorry. And indeed, we can further divide this circle. We have pi by 4 equal to 45 degrees, which would also be equal to 50 gradians, or equal to 1/8 of a revolution. But this isn't the full definition of a radian. The mathematical definition of a radian is simply this. A radian is defined as the length of an arc divided by the radius that subtends said arc. So an example, we have an arc length, we'll say 5 meters, and this arc is subtended, so the center point or the focal point of this arc is 2 meters away. We have an angle theta. What is theta? Theta equals 5 meters divided by 2 meters. The length of an arc divided by the radius that subtends the arc. 5 meters divided by 2 meters, which is equal to 1.5 radians. And it's written just like that, radians. However, in a mathematical sense, we actually don't need this unit here because this is meters per meter. We could also write this as 1.5 meters per meter, or just 1.5. You will often see that radians are written without the unit next to them, because a radian is basically the unit measure of angles in mathematics, and essentially do not require the unit to be written directly next to it, as it's implied to be radians if no unit is given. If no units are given, assume that the unit is going to be in radians. So we can see here, this is just one application of radians. If we want to calculate what this angle is, given the length of an arc and the radius subtending that arc, we calculate the angle. We can then convert this to degrees, gradians, revolutions, whatever we want to convert it to using the appropriate conversion factor. And those conversion factors we can give here. 1 radian is equal to 180 degrees over pi is equal to 200 gradians over pi is equal to 1 revolution over 2 pi. We can see these are just the radii of the circle that we gave above in the definitions of these angular units of measure. So indeed, the degrees, the radius, is 180 divided by pi. What we've done here is we've taken the circumference, which is effectively an arc length, and divided it by 2 pi to get the radius. But if we were to take if we were to rearrange this exact formula, we would find that C over R equals 2 pi for a full circle. We've done the same thing here with gradients, and we've done the same thing here with revolutions. So essentially, these conversion factors to radians come from the definition of these angles given on a circle. And it makes sense to define it as a circle. If you have a protractor, for example, a protractor is basically a semicircle in which you have the various degree markings. So it makes sense to define these in terms of a circle. In addition to being able to calculate radians directly from an arc length, we can also calculate an arc length based on radians. So here we have an example of attempting to find the arc length given an angle and a length, or a radius in this instance. So this radius, L, is 2 meters, and we're given that the angle that subtends this arc is theta, equal to 90 degrees. So there's a couple ways we can solve this. We can either solve this by noting that 90 degrees is 1/4 circle, and thus we can calculate, based on a full circle, circumference of a full circle is equal to 2 pi r, which in this case is going to be equal to 4 pi. And so dividing that into a quarter circle equals 1/4 times 4 pi. So 1/4 circle is going to have a length of pi. So then we find that A equals pi. Using radians, we know that 90 degrees equals pi by 2 radians. We know that from the definition of radians, we can multiply the angle by the radius to get the arc length. So we can say that arc length A equals, in this case, L theta. We know what theta is, we know what L is. The arc length is equal to 2 times pi by 2 equals pi. And indeed, this is a more powerful formula. So arc length, the length of an arc on a circular path, is equal to the radius multiplied by the angle. So this is applicable in a lot of engineering problems as an example. If you have a circular path and you want to know what the arc length of that path is, based on radius and angle. Additionally, you can use this for computing an angle based on an arc length. So you have a certain arc length of material. You want to have a specific radius. You can figure out how much of that angle, theta. We're just going to give some example problems, which will kind of help you get the idea of radians. So in this example, we have a jogger running from point A to point B along the path shown. So they're going up, going basically counterclockwise from point A to point B. They're jogging at a speed of 1 meter per second. And it takes them 1 minute to get to point B. We're asked to find how long it takes the jogger to get around the track, as well as what distance they cover in that duration. So this is a classic example involving radians. We could solve this using degrees. We could solve this using gradients. We could solve this using revolutions. The point is, solving this with radians is going to be considerably easier than solving this by converting into degrees or converting into revolutions. And in general, it's good to be able to solve this problem using any 3 of those, or any 4 of the units of angular measure. So we know that they're jogging at 1 meter per second, and it took them 1 minute to get to point B. Thus, we know the arc length. A equals 1 meter per second, and 1 minute is equal to 60 seconds. So that's equal to 60 meters. This is something that you'll probably learn in your physics courses as well. We know that the radius we were given, the radius is 20 meters. So given the radius and given the arc length, we can define an angle theta. I'm going to do this in red to show that it's something I've added afterwards. We'll define an angle theta. And we'll say that theta equals arc length over radius, which is equal to 60 meters over 20 meters, which is equal to 3 radians. So we're asked 2 questions. How long does it take to get around the track, and what distance do they run? Well, we can pretty easily figure out what distance they run. We know that the track is a circle. It's a circular track. So one full track is 2 pi r. So C equals 2 pi times 20 meters equals 40 pi meters. And you can just leave it as pi. You don't have to convert it to 3.1415926535898, etc. You can just leave it as the symbol pi, and that'll essentially allow you to keep your accuracy throughout the problem. You won't be losing any significant digits. So the full track length is 40 pi meters. So the distance that they run. Now when you go to actually write out the conclusions to this problem, you will want to convert this to decimal simply as your final step. But for all intermediate steps, it is best to keep it as pi. Only convert it at the final step once you've solved the entire problem. How long does it take? Well, this is a very easy one to solve. They're jogging at 1 meter per second. So we'll say v equals 1 meter per second. In order to determine the time that they've traveled, it's basically going to be the distance divided by the velocity. So t, because essentially velocity equals distance over time. Therefore, time equals distance over velocity, which is going to be equal to 40 pi meters divided by 1 meter per second equals 40 pi seconds. So therefore, the jogger has traveled 40 pi equal to approximately 125.664 meters and took 125.664 seconds because essentially this is a 1-to-1 since the velocity is equal to 1 meter per second. This is a very simple example. This is also a terrible example because we didn't end up having to use radians at all. We could rewrite the question to ask how much more time or how much more distance needs to be covered to complete the track, given that they were already starting at an angle of 3 radians. These are the sample problems that you may solve. The answers are in the description of the video. So first, complete this table. So we have a bunch of unknowns in this table. Just basically go through and do the units conversion from degrees or revolutions or radians to the other two. That shouldn't be too difficult. Question number 2, you're given a figure. This figure, it's a pretty figure. It took a long time to draw it. You're asked to find the unknown quantity. So you're given a radius r, an angle theta, and an arc length a. So based on what you're either given a radius or an arc length, or an angle and a radius, or an angle and an arc length. You're asked to find the unknown quantity, the one that's not given. And the third question is, if you're driving, is more an application question. If you're driving a car and you're turning, the inside wheel travels less than your outside wheel. Now you can think of this in terms of the arc length that we've described here. Obviously, if you're turning, then one of your wheels is going to be on an inside radius, one of your wheels is going to be on an outside radius. I've also illustrated that here. So given the difference in radius, for the same angle that you're turning, 160 degrees, you're going to have a different arc length that each of those wheels travels. You're asked in question number 3 to determine how much further the outside tire has traveled compared to the inside tire. So if you have any questions, feel free to leave them in the comments section below. Aside from that, I'm Arlington Matrix. This has been a quick, short introduction to radians as a form of angular measure. Thank you for watching and have a great day.